Hello everyone, this is Codyssi day 15. We have still one day to the end of the challenge. Today I recorded this. I didn't record the live solution as it took me longer than usual because I wanted to revise a little bit C++. So today I present you a C++ solution. So if you're interested, you find the code in the GitHub repo. And basically what we're asked is, in the first part of the problem, we're given a set of items and we need to create a binary search tree based on the IDs of the items. Basically what you do is you take the first item as the root, then you go through every other item in the list, in the order of the list, and then you have to insert these items in order. So for example, you take this one and you want to insert that one item. What you do is you start from the root in this case is the first item, and you go either left or right based on the fact that, like, if the ID of this is smaller than the ID of the root, then you go left, otherwise you go right. And you do this until you find a suitable spot, so basically a node that you still don't have, and as soon as you do that, as soon as you find the node, you just insert the item. And this is just part one. So part one, you build the tree and then you're asked to BFS the tree that you constructed and basically make a sum layer by layer. So you have to sum the first layer, sum the second layer, so sum the IDs, and then you have to find the maximum sum between the layers and multiply it by the number of layers. So basically you have your tree like this. You have to do the sum layer by layer. So this layer, then this layer, then this layer. Let's say that this is the maximum with a value of 78. The final answer will be 78 by 3, because 3 is the number of layers. Second part, what you're asked is to just create an extra item, so an item with this ID. You're asked to insert it in the binary search tree, and then you just have to print the path to that node. So let's look at the code a little bit. So this is my code for part one. As you can see, I created a attach function that takes in input a pointer to the target, a pointer to the root, and then this function is recursive, so we always call. So if we find a suitable spot, we insert the node, otherwise I just call the attach function recursively. And once you do that, it's just a matter of parsing the input and then creating a node for each item in the list. You create a new node and you attach it. So very straightforward. And then for part two, you just create the new node and then insert it and print the path. So I slightly modified the attach function to also keep track of the path to the node that you insert. And then, so for part one, obviously you also have to BFS, but this is not really I mean, it's a standard BFS. The only thing is you need to go layer by layer, like you have to do sums layer by layers. So in this case, what I like to do is just use 2 queues. It's not very efficient, but it's the most intuitive way that comes to my mind when I have to do this stuff. And I just instead of putting items in the main queue, I put them in a temporary queue, and then I copy the temporary queue in the main queue when the main queue is finished. So when I have to do stuff quickly, this is the most intuitive way for me to write these sort of things. And then for the last part, which was the interesting part, you had to add this, like to consider these 2 extra nodes. These 2 are 2 items that are already in the first list here. And so for example, this one is this one, and this one is this one. You have to find the lowest common ancestor between these two. What does it mean? Basically, let's say that we have our tree like this. Let's say that our two nodes are this one and this one. We have to find the lowest common ancestor, which in this case is this guy. So it's the ancestor, it's an ancestor of both T1 and T2, and it's the one that is the farthest away from the root, or in other words, the lowest in terms of height. So in this case, you just DFS through the tree. When you basically stumble on either T1 or T2, you return yes. If you are on a leaf, sorry, if you are in a null pointer, you just return no. If you receive two no's, you return a no. If you receive a yes and a no, you return a yes. If you receive two yeses, then you are the answer. So this guy knows he is the answer, and it will return his own ID. A node, when he receives an ID and a no, it will return the ID. This is just how you solve lowest common ancestor, and this is the C++ code. So this code right here. There's probably a more efficient way to do this without strings, but this, I think, it's the most intuitive one. And that's just it. You have to find the lowest common ancestor, and that's the output of the solution for part 3. See you tomorrow for the last day.